So welcome back, everyone. And then this is an 8-week workshop on Industrial Internet of Things. It's sponsored by the UMI Metal Casting and Foundry 4.0 Center. During the presentation, please mute your audio and ask questions in the chat window. You may turn on your microphone after the presentation for questions. And the video will be recorded and sent to you once it is ready. Okay, so let's get started. Okay, so the PowerPoint slides are available in this link, which is in a Google Drive. So you should be able to access the PowerPoint presentation, the file, the slides in that drive already. Okay, so today is the first week of the workshop. Today we'll discuss some commonly used sensors and sensor interfaces. And then starting from next week, we will go through 4 projects. Okay, here's the outline for today's presentation. We will first discuss 2 different signal types, analog and digital, and the common hardware interface protocols between sensors and microcontroller boards, including integrated circuit or I2C, and then the serial peripheral interface, SPI. Okay. After that, we'll go over some commonly used sensor boards and then some adapters, and then see some examples how to use them with the Raspberry Pi, and then one Arduino compatible board, the Node MCU. Okay, so that's the outline for today's presentation. Okay, so signals can generally divide into 2 different types, analog and digital. The difference between those 2 type of the signals can be seen in this figure. In this figure, we can see analog signals have the smooth, continuous change, while the digital signal operates on the discrete states. Okay, so typically like on, off, high or low, and then represented typically using 1 and 0s or in binary. Okay, so not like a decimal, we have represent digits between 0 to 9, but binary only have 1 or 0, 2 different digits. Okay, so for the digital signal, one typical example you can think of for the switches, you only have 2 states, on or off. Okay, on or off, nothing in between. That is the difference between those 2. So for the digital inputs, you can think of some of the sensors have those kind of digital outputs, and those can become the digital inputs to the microcontroller board. For example, proximity sensor, they can output a low signal when it detects an object within its detection range. And then when there's no object detected, then they're going to output 1. Okay, so that's a like digital signal, 1 and 0s. And then the microcontroller boards can also generate outputs to control action components. For example, turn on and off LEDs, or control actuators. Okay, an actuator. So the microcontroller and for example, the Node MCU, and then the single board microcomputers like a Raspberry Pi, they can work with the digital signals easily. Okay, because those microcontroller or microprocessors are all digital devices. They can easily dealing with 1 and 0s. And they can interfacing with sensor outputs if it is in digital, easily via there's a general purpose input and output, or we call it GPIOs. For example, the Node MCU has totally 17 GPIOs, while for the Raspberry Pi for Model B has a total of 26 GPIOs. But not all of them can directly work with the analog signals. One thing, when we're dealing with digital signal, we still need to be careful because some of the sensors, typically traditional industrial sensors, they may need working with a voltage range outside of that microcontroller can work with. For example, if your sensor are working with a voltage between 0 to 10 volts, while your microcontroller, like Raspberry Pi and then Node MCU, typically work between 0 to 3.3 volts. Then you got to be careful, okay? You need using some of the mechanism to shifting that voltage, okay? 0 to 10 volts to 0 to the 3.3 volts, so they can work with each other. Otherwise, if you try to directly connect them to each other, you may damage the microcontroller board. Okay, so that's about digital signal. For the analog signals, we know that most physical signals in the world by nature are analog, such as temperatures, pressure, resistance, moisture. All those are actually what kind of analog signals. So the transducers or sensors will convert those physical signals to electrical current or voltage signals. Those also are analog. That analog signal, those electronic analog signal typically still are in what? Those electronic signals still in analog, okay? The signal may change in the time domain. The signal may change slowly, such like, for example, from a thermocouple output, that voltage change may not be that rapidly, and then some may change faster, such as, for example, the electroencephalography or the EEG signal, and those are the some signal working in time domain. Some signal may also working in the frequency domain. That means information is represented or contained in its frequency information. Okay, so in order to convert it, no matter what kind of analog signal, if we need to have those to work with a microcontroller, we need a device called the analog to digital converter. Okay, we need a converter to digital signal so that microcontroller or process can handle it. Okay, typically the microcontrollers, many of that microcontrollers, especially for the embedded system. Okay, those microcontroller used for the embedded systems has ADC integrated. Okay, for example, like Arduino MKR Wi-Fi 1010 board, which including one 12-bit and ADC can support up to the 20 channels. Node MCU with the ESP32, they could also support up to, I believe, it's 15 channels and with 12-bit of the ADC, okay? But Raspberry Pi itself does not accept the analog signal and then needs some external ADC board attached to the Raspberry Pi so that it can work with it. All right. So, and we talk about the 12-bit. What does that mean over here? 12-bit ADC. So, the bit, when we talk about the, is that the number of the bits is used to represent the input analog signal. We talk about bit all the time. For example, like okay, the when we subscribe to ISP, okay, they will said, for example, AT&T, they said, okay, the data rate I'm going to provide is 200 megabps. So what is the megabps? BPS stands for the bit per second, right? So the bit is just one digit of one or zeros, one bit of the binary. The bit stands for the one digital in binary. Okay, so that's the bit. So if we convert an analog signal to the digital, we will represent that as shown in this figure. Okay, we represent any analog signals represent using some bit, okay, so some binary values simply. So if we talk about 10-bit ADC, meaning we're going to use 10 binary digits to represent the corresponding analog signals. Okay, so typically we can see the commonly used ADCs nowadays you're going to see is like 10-bit, 12-bit, or 16-bit ADCs are pretty common. Then they could also have a really high resolutions, like audios. They could be stored in like 24-bit, and then the more of the number of bits you used, okay, we can see that the small of the incremental voltage that it can be recognized. Okay, so the small of magnitude of the quantization error you can have. Okay, so that though in the other hands, then you're going to need more bit. That means what, more processing capability needed, and then storage that data need more spaces. Okay. So the 4n bit of the resolution of the ADC, the minimal of the voltage change can be detected as given by this equation. V is reference voltage, or we can consider the maximum allowed input voltage, divided by 2 to the n. N is the number of bit to represent the analog signal. So for example, if my voltage is between 0 to 1 volt, okay, and I use 10-bit ADC, meaning you will have 1 volt divided by 2 to a power of 10, which is 10 or 24, right? Roughly around 1,000. So roughly you'll be able to detect 1 millivolts change. Okay, that's the case. So you got to be consider that, okay, what is that resolution you needed for your ADC? That depends on your applications. Okay, so this is one thing. Okay, quick question then. Which ADC will allow the detection of 1.6 millivolt change in a signal if the input range is between 0 to 10 volts? So again, just using the previous equation giving, right? That means, what's your answer in this case? Anybody? B, yes. Great, good job. Okay, so the answer should be actually 16-bit ADC is needed if you want to be able to achieve that purpose. Okay, great. So for the analog signals, sometimes may also require signal conditioning, okay, depending on what you have. For example, like for the thermocouples, you may need to have the amplification and also some the cold junction compensations. So it really depends on what kind of sensor you use. However, most of the time, the sensor boards you're ready to use are including the conditional circuitry and then ADC circuitry. So they converted the signal to result to the digital already, and then communicated that digital, okay, signal with that microcontroller directly. Okay, so that way, you can communicate or with the microcontroller and transfer the information to the microcontroller easily, and then also more immune to the noises in the environment. So next part, then we will look at some hardware communication interfaces. Okay, the company used the hardware communication interfaces for the are listed over here. So the first one is the UART, Universal Asynchronous Receive and Transceiver. Those are really commonly used, one of the most commonly used interfaces between the MCU and the external devices. Those use serial communication. And then also the integrated circuit, or we call it I2C, or sometimes we also write it as I2C or IC. And then that serial peripheral interface, SPI. So today we'll just discuss the I2C and SPI, okay? Because those are really commonly used to interface with the sensor, and then those off-the-shelf microcontroller boards. Okay, so let's first look at the I2C first. I2C is a synchronous controller and target type, and they support the single-ended serial communication. What is the serial communication? Serial communication means I'm going to transmit 1 bit at a time, okay? 1 bit at a time. And it is created originally by the Philips Semiconductors, and then later on acquired by the NXP Semiconductors. So it is designed with the goal to connect low speed or low data rate peripheral ICs directed to a processor on the same PCB board. Okay, so next to each other, basically, within very short distance. And it's really popular. The main reason is due to they only need 2 wires. Okay, so it's very easy to make the connection. Only 2 wires needed, one for clock, one for the data. Okay, and it has to be implemented over thousands of different IC manufacturers, more than the 50 companies. So, and that's why also they are very popular. So let's look at how the I2C devices are connected. We can see over here, they're going to have a microcontroller, and we call it in the standard, they call it as a controller. Used to be called master slaver, and then now they change it to the controller target. Okay, so anyway, each devices, all the devices are connected to the controller through what? There's 2 lines. One SCL stands for the serial clock. Another one for the data is that serial data. Okay, and then the device, the target devices will has a unique 7-bit address. So there's totally 112 different addresses available. Okay, and each device is connected to that I2C controller has a unique 7-bit address. Okay, you cannot have like, oh, device 1, device 2 has the same address. Then they're going to cause the issue because they don't know who is who anymore, right? So the controller node, the controller or the microcontroller in this case will be either your node MCU or your Raspberry Pi is going to provide the clock signal and also initiate the communication with the target using that assigned unique address. So they basically will tell you, okay, now the address 0x18, please send me the data, okay? And that's it. So the data rate, the standard is up to, in a standard mode, that's mostly common, you see, is up to 100 kilobps. So it's not very high data rate. However, it will be enough, really sufficient for most of the applications. Okay, so for example, your temperature is not going to change that fast. You'll probably only need to check the temperature, see maybe one sample per second or per 15 seconds, right? So you don't really need that high data rate. That is one good thing. Really simple connections, and then you could do that. So how are you going to check that I2C in the Raspberry Pi? You could use this command as showing over here, sudo I2C detect and -L. Here is a lowercase l, just not one, not I, not uppercase I, but a lowercase l, okay? And then you type in, they will display what kind of device available. And you can also check what kind of I2C devices are connected to your currently to your Raspberry Pi, okay, Raspberry Pi. So once you connect, you can see, for example, in this case, we're showing that actually what has one device connected with the address 0x77. So typically people want write of the address 77 that is in hexadecimal. So it's not decimal number, but in the hexadecimal. So in the binary is actually represent this value. I think I have a one. I think that is, sorry, because I think I need to collect this. This should be totally 7-bit. So I put the one extra 0 over there. Okay. So it should be 1110111. Okay, so totally 7-bit. So that's the address you're going to use, and then we will also show examples later. So this is for the I2C protocol. Now let's look at how the SPI works. Okay, Serial Peripheral Interface SPI, originally defined it by the Motorola, but now also acquired by the NXP. And it is a synchronous full duplexed main subnode type of interface. So we see the I2C is not a full duplex, it's actually a half duplex. What does that mean? Is that between your controller and then the target, they can send in both direction, however, not at the same time. So the target or the sensor can either receive an instruction from the controller or sending the data to the instruction, but not in both directions at the same time. SPI does provide that, okay, allows full duplex, so you can transmit data and then receive the data at the same time. So, they will require more pins, obviously, in order to achieve that. So you're going to see over here, they need a 4-pin connections. Also needs a clock. You see over here, that's the SPI clock. The main, which is your microcontroller, will provide that signal to the sensor or that other external devices. And then they have your main in and subnode out. So they will send the data from subnode to the main, or send that instruction from the main to the subnode. Okay, so that's a fully duplex. And the last one, the signal needed is the chip select. Okay, chip select, and sometimes also denoted as the SS, but they mean the same thing. Okay, so there's have 2 different ways to connect it one main to the multiple subnode. Okay, and this is a regular mode. So you can see over here, this the main microcontroller, they can connect multiple of them. So individual nodes will also have that chip select signal that is controlled by the main microcontrollers, and they're going to select this subnode at a time. You could also use a multiplexer to generate a chip select signal, because you cannot, those two are sharing that data bus with the main node. So they cannot have two subnodes work at the same time. Okay, that is going to cause confliction and data corruptions. Okay, so that's that regular mode. You could also work with the other way we see over here is the daisy chain mode. Okay, so we can look at over here this daisy chain mode, that chip select signal over here, the CS, is tied together, and the data probably going to propagate from one subnode to the next subnode, and all the subnodes going to receive the same SPI clock at the same time, and which is going to be connected easier if I need lots of subnodes, okay, in that case. So those are two different ways. Now we are looking at some sensor boards and interfaces, and also some of that examples. Let me turn on my light. Yeah, okay. Okay, so today we will then look at some of the sensor boards and then adapt examples. First one, we'll look at the BME or the BM 280 or 680 sensor board. And then we may also have a look at the MCP 9600 adapter for thermocouples. And then we will also quickly go over with the analog to digital converter ADS 11115. If you want to work with the Raspberry Pi, you need some ADC board to work with that some of the sensors that has the analog signal output. Okay, and I also include in the slides for this Hall effect sensor, but I don't think we'll have time to go over it. And then Pi plates. The last part of this presentation, we will also talk about how we can interface the BME 280 with Node MCUs so that Arduino IDEs. Okay, so for the example code, which I uploaded into this GitHub, so link to that one, you can also download the code, and then and then you can also look at the source code, which you can download in your computer or to your Raspberry Pi. Okay. So first, let's look at the BME 280. Okay. So the BME 280 and the BME 680, they are very similar. Both are from the Bosch Sensor Tech company. They are very small size and ultra low power consumption and low cost. For the BME 280 is slightly cheaper, and then they can measure relative humidity, pressure, and also the ambient temperature. So the temperature range is like not really a very wide range. They semiconductor devices, so they could only working with the -40 to the 85 Celsius degrees. While for the BME 680, in addition to what BME 280 can detect it will also be able to provide some of the volatile organic compounds or the VOC information for that air qualities. Okay, so for the sensor itself, they provide both I2C and the SPI interface. They can act as a target or subnode in both protocols. So typically, you can just using this board and make your own PCB, but most people not going to do this. You can just easily purchase an off-the-shelf board online, okay, like from the Fluid or Amazon. Okay, so although they both support the SPI and then that I2C, I see most of the applications for the I2C will be sufficient. So for the board, they actually support 2 address. Remember, we see the I2C, they will have need a unique 7-bit address, right? For this BME board, the 280 board, they are typically using address either 0x77 or 76, depending on a few configurations. So you can look at datasheet, and then typically the board, they will provide one default address, and you can make a slightly change to the board, okay? For example, the SDO, if you change the default connection of the SDO in this ADA fluid board, then they will change the address to 0x77 to the 76, okay? So we will first look at working with this BMI 280 on the Raspberry Pi first, and then we will also at the end, we talk about the Node MCU, okay, to interface with BME 280. Okay, so the first thing first, we know we have a need two wires, right, to make the connection for the I2C. So how we're going to make the connection? Here's the hardware. So we're going to use that connection over here and the GPIO2 and then GPIO3, those 2 pins. You can see also here, over here is serial data, SDA, serial clock. So those are the pins easily could be used to work with the I2C. So we will just connect those I2C to the I2C pin of the sensor board on the BME 280 board. And BME 680 has a pretty much exactly same pin layout, just connect the same way, but you'll be able to also detect VOCs. Okay, so in addition to this, you may also need to connect the power supply and the ground. Those 2 pins are also needed for the connection. That's for that Pi 0W. And then the good thing about Raspberry Pi is no matter which board you are using, there interface, those GPIO pins are all the same, okay? They maintain the same so that you can easily do the same configuration. So this is for the Raspberry Pi 4 models. Those are the 4 pins. I mean, you don't have to use this ground. You can also use the pin 9 for the ground or the pin 25 as the ground, which all works okay. But you have to use 3.3 volts for the power supply, okay, to the BME 280 or the BME 680. And you got just be careful because that voltage range they can work with is up to 3.6 volts. So they are not be able to work with the 5 volts, okay? So don't use the 5 volts power supply. The ground pins are okay. So the connection, what you're going to make the connection is like over here, this just one examples pin, those 2 pin 2 and 3, okay, over here. are going to be used. One for the data and the one for the clock. So SCK is the clock, and SDI over here is for its the data, serial data, okay, serial data. And then you see the name is slightly different sometimes because those pins are also used for the SPIs. They may also use for the SPIs, but in the cases, you're going to also use the SDO, okay? And then the CES, okay? So you're going to need 2 additional pins if we use the SPI instead of I2C. Okay, so that's the connection. If we're using this ADA fluid board or other boards, you have to check what's their default configuration, because the BME, if you see over here in this middle, okay, the BME to 80, and over here, this chip itself, they are designed with 2 address with 1 configure pins. Okay, so the I2C address can either be 0x77 or 0x76. Where we see over here 0x77 by default is talking about the ADA fluid BME 280 board. Okay, so that's one thing you got to be really careful. You may need to adjust the code slightly using different address. So for example, if you're using this address, you're using this board, okay, it's a board from Amazon, then the default address for this one based on the configuration is actually 0x26. So that's one thing you need to be careful, okay, need to be careful. So again, over here, that the board you need to supply the power I mentioned earlier has to be up to the 3.6 volts, no greater than that. Okay, so got to be careful. You don't want to supply 5 volts to it. You may damage the board, okay? So once you connect it, if you would like use this STEMA QT 4-pin, you could also getting this connection. There's some of other boards which you could, both side has that STEMA QT 4 pins that could also make some connection. Another thing I want to mention over here is you make sure you want to shut down when you make these hardware connections. You want to shut down that Raspberry Pi first. So before, okay, you want to power off the Raspberry Pi before you start to make the hardware connections, okay, just to be safe, So that's one thing. Once you finish this, then you can install this Python library for the BME 280. So once you do this using that, the condition is you have to install that circuit. We're going to use the circuit Python, so we have to install the ADA fluid blinker library first. So you need to check that works. And then after that, you can install that BME 280 library that you can work with, okay? So it may take a few minutes once you're done with it, and then you can do the test, okay? So the example code, which you could getting just through this link. So for example, okay, I will show you. Okay. So if I have this, you can just copy this. Okay. Going to copy. Yeah, just a copy of this copy this command, okay, which actually will obtain that file from the GitHub automatically. Okay, so for example, if I just want to get in this one, so over here we have two files, right? So we can just use the yeah, so we can just over here. I want to make sure those are in the same line space. So over here, sometimes they have some recognized symbols when you copy paste, and I will just getting the file, okay, because I already have that file already, so good. Okay, I can delete the file. Oh, I am sorry. That's Windows command. Okay, so if I remove the file and then trying to re-get it, and then they what happen? Nice. Oh, okay. Here's unwanted space. Yeah. So I should be. So you can see it saved the file, and I could just run the command, and then the file should be able to, the system should be run this demo code, and then it will just acquire the temperature, pressure, and then humidity signal from the BME280 sensor directly. Okay, so over here we can see is just running, and then we have for downloaded two files. One is just a demo of the BME280. Another one is the save data locally. Simply, we not only store the data, but not just display the data, but we also store the data into a local file, okay, text file, so that you can later to check it, okay? So for example, if we go back to this one, okay, the programming setting to sensor to getting the data every 5 seconds. So if I'm going to just stop over here, and then I could see, check if what is the local file I have, 2024. Okay, so this is the data we just stored, and I can see what are the information in this one. Okay, it's a really small file, so that should be no big issue. So I just only for the a few lines of information this morning, right before the workshop, and then now. Okay, so those are the data we checked, saved in the file. Okay, and then in this one is showing some explanations, and you can check. Okay, so we could also and later on we will discuss how can let the system automatically run and then save the data on the back instead of we have to call the Python command in the terminal window. Because otherwise, in this case, when we exit from the SH3 terminal window, the program ends, right? So we'll discuss that one next week. So let's look at another similar thing is for thermocouple. We're going to use that MCP 9600 board. This is the board, and then you could use different channels to connect it to that. You can choose multiple of the addresses to work with, okay, which addresses, which you can choose 4 channels. So you can choose different addresses if I need to work with multiple thermocouples. Okay, so here just showing one examples I can connect to a thermocouple, the board. And similarly, I can use the same connection. So again, in these cases, we are connected to pin 2 and 3, one for the clock, one for the data, okay? Serial data and serial clock. That's a connection, pretty straightforward, they can work with, okay? Again, you want to shut down your Raspberry Pi before make any hardware changes. Here's just showing the figure, okay, how we can connect this. And two boards, both are through the I2C connection, okay, through the I2C interfaces. And then once you do that, you should be able to see, okay, there's using I2C detector -Y1, then you will be able to observe. Now you have two devices connect to your I2C bus, okay? Connect to I2C bus. One is on address 66. That's for my MCP 9600 for the thermocouple. And the 77 is for that BME 280, okay? So we could do the pretty much the same thing, install the library, okay? You can copy the command and then do the same thing and show the demo. You'll be able to just test if we'll be able to work with your Raspberry Pi, okay? And then if you want to try another one, I can work with both the BME 280 and then thermocouple, the example also giving in this demo code. Okay, so you can modify above it. Next one we're showing over here is a moisture sensor. The moisture sensor over here, the output is analog voltages. So we cannot interface with the Raspberry Pi directly. Instead, we could use some ADC board. Here we use the ADS 1115. This is very cheap and they have a 4-channel program gain amplifier, and then they could support 16-bit, right? ADC. They support 16-bit ADC. So I2C address, you can see over here, is within this range. Here's showing the connection. Again, you need to have a ground and then a power supply connected. Again, you signal, or again, you want to power off your Raspberry Pi if you need to make any hardware changes, okay? Just shut down and then power off your Raspberry Pi. Use the shutdown command, sudo shutdown command to shut down your Raspberry Pi, and then power off, and then you're going to make the hardware changes, okay? So you could also install then that ADS 1115 X5. They could have support different devices. So in this case, you see I have 2 more devices are added. Okay, added. So that is for the ADS 1516, and then you could go through the same process and try it out. That's another example. So the GPIO Hall effect sensor, similarly, I also would like to mention the Pi plates, because many industrial sensors or transducers does not work with the 0 to 3.3 volts, right? Simply that's not the case. So there's some company which also provide adapters so that you can work with many different kinds of sensors. They supported, like for the industrial use, they supported some of the board using a 24-bit of the ADC converters, so really high precision one. High resolution, okay, provide very high resolution, and they can support up to the 30 VDCs, so it's more common for the industrial use, okay. You can also consider there's also have the code examples. You go to the piplates.com Okay, that's some additional information over here. The last one, I know I'm on the time, but just quickly go. But last one, we want to work with the Arduino IDE. So this is a Node MCU board. How we going to connect you with the BNE 280? Very similar. Okay, very similar. So the Node MCU itself is a single board, does not has a operating system inside of it. So it's more of the microcontrollers. We can use the Arduino IDEs to program the code to it. And then again, you can see the data, okay, printed out in there's a serial monitor. Okay, serial monitor, that's the information transmitted back to your computer and then displayed to the users. And later on, we will discuss also more examples about this using this Node MCUs for applications, okay, for the IoT applications. Okay, so that's pretty much for today's presentation. Basically, we discussed some examples how we can communicate with between your sensors with a microcontroller or single-boarded microcomputer like a Raspberry Pi through the hardware interface protocol, I2C or SPI. Okay, any questions? Any questions? And the next week for our projects, you will going to need a BME 280 and also the Raspberry Pi. Okay, that's the two things that you need, a headless Raspberry Pi. Any questions? If not, and then that's it for today. Okay, we'll see you guys next week. And then if you have time, please, you can send up comments or any questions or requests through the survey. Thank you. Bye-bye. We'll see you guys next week then.